All right, now we're back from the FET. We've probably got immensely confused by that, so hopefully we'll clear things up because we're going to talk a little bit here about isotope abundance. Every element on the periodic table, almost every element, has multiple isotopes that are found in nature. Some of them have 2, some of them have 3, some of them have as many as 8. One of the best ones I know of has 8 is titanium, for example. And when we look in nature, we see that in every natural deposit, right, that is every deposit we find in nature, there is an amount of each isotope in that natural deposit, and we call the amount of each isotope the isotopic abundance or isotope abundance. You hear some folks call it natural abundance. Natural abundance sounds too much like nature, and that sounds too much like biology to me. And me and biology never got along very well, so I prefer to call it isotope abundance. It's always reported as a percentage of the number of atoms that are in a sample. For example, the abundances of uranium that I talked about before, 234 is 0.01%, very small amount of 234. 235 is 0.72%, and that means that 238 is the vast majority of a sample of uranium, is 99.27%. So those are the isotopic abundances for all those uranium isotopes. And what we do is we take those abundances and we can calculate average atomic mass, right? If you look on the periodic table, you see all of those masses down at the bottom. They all have decimal places. And as you answered in the FET, that doesn't really make sense, right? How can you have 0.1 of a neutron or 0.1 of a proton? Doesn't make sense at all. So the mass that you see there is actually an average of all the atoms in a sample of that element. And if you round that number to the closest whole number, usually, not every time, but usually, you get the mass of the most abundant isotope. It's not always the case. It is the case in uranium. To calculate that average atomic mass, what we're going to do is we're going to use this equation right down here, way down there. There we go. Average atomic mass is equal to the percent of the first isotope times its mass plus the percent of the second isotope times its mass plus the percent of the third isotope times its mass plus the percent of the fourth, yada, 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 and so on and so forth, right? That's what these dots mean, is this could go on forever. The most you'll ever see is 8, right? Because the most I can think of a natural occurring element having is 8 isotopes. What's interesting here is I'm going to go ahead and throw this one in here. You hear me saying naturally occurring? That is done by nature. Human beings can actually make isotopes, and we'll talk about those at the end of the semester. But we don't include those in these calculations. If it's man-made isotope, it doesn't get included in these calculations. So let's look at an example. The example I'm going to use, why not uranium? It's one of the most famous ones here. So to do this, we need to calculate the average atomic mass. We're going to take that percent abundance, and we're going to move it down here. Now, you notice when I move the percent abundance, it's no longer 0.01. It's 0.0001. Why is that? Well, remember up in the chart, it's reported as a percent. Now we're going to start doing math with it, so we have to convert it from a percent to decimal notation, right? So check that out. So I don't care which mathematical way you use to do this, whichever way you look at it, you can either move the decimal place over twice, or you can divide by 100, right, to get, because there's always 100%, right? Doesn't matter which way you think about it, but we're going to take that number, we're going to move it down here. Some folks, kind of weird folks, even will just put a divided, 0.01 divide by 100 down here. Whichever way you want to do it, that's fine. We're going to multiply that by the mass of this isotope. Gee, what's the mass? Well, it's right there in the name, uranium-234. So we'll pull that down here. Add to that the same stuff for the second isotope. Again, we've got 0.72. Oops, did them in not quite the same order. 0.72 divided by 100 is 0.0072 times 235 plus the abundance of this one, again divided by 100, right? So we get 0.9927 times 238. Plug all that into your calculator, and you can plug it in just like this, 0.0001 times 234 plus 0.00072 times 235 plus 0.9827 times 238, and you get 237.98 AMUs. Now here's where things get weird. You want to check your work, so you decide to go to the periodic table. And you look at the periodic table, and the periodic table, if I can scroll back up real quick to my periodic table right here, here's the periodic table. You look at uranium, it says 238.03. Wait a minute. What the heck? We didn't get 238.03. We got 237.98. How in the heck does that work? Well, not the exact same number, but they're pretty darn close. And one reason for that is when we did our calculation, we use actually atomic mass, and technically we use the number, right? Which is just counting protons and neutrons. And that assumes that they're both identical in mass. As it turns out, they're not. What actually we see is that the neutron has a mass that is 0.1% higher than that of a proton. So if you want to, you can go through and you can actually figure out a way to include that neutron mass in there. But otherwise, you just have to accept the fact that the more neutrons there are in an atom, the more the average atomic mass will be off. What we also see happening, strangely enough, is as you add more and more neutrons, the mass kind of deviates a little bit. We call that mass deviation. We're not going to worry about that in this class, though. We're just going to accept that what the table says is real, and the reason that's real is because what's measured there, the number that they actually measure, right, actually includes that mass deviation. Really weird stuff. We're not worried about that. I just want you to be able to use the calculation. So we're just going to use A in our calculations for this class because it's why you're already in chemistry. Why make your life more difficult, right? So now you can calculate average atomic mass, and now you can move on to the average atomic mass homework that is assigned.